So my talk is going to be about the introduction to space and atmospheric studies from Arecibo. So our Earth is a very unique planet. I will remove this one. So Earth is a very unique planet and it's part of the solar system that you all are familiar with. And this is unique because Earth can sustain life that no other these planets that are very close to Sun and us. It's still like we do not know if they can sustain life the way the Earth does. So today I will be discussing about how we study the Earth's atmosphere and ionosphere system. So the outline of my talk is as follows. I will first give the brief introduction about the Earth's atmosphere, where I will discuss about different layers, both in atmosphere and ionosphere. So when we use the word atmosphere, we usually refer to the neutral part of the atmosphere. And when we are discussing ionosphere, then we are discussing about the charged particles. And what are the techniques that we use to probe the different layers of the atmosphere-ionosphere system? So there are two kind of ways. One is called active remote sensing, where we are actively transmitting electromagnetic wave to the atmosphere, and then we monitor the backscatter signal. And this is done by two instruments, which are called LiDARs and radars. Then there is another way, which is called passive remote sensing. So in passive remote sensing, what we are doing is the instruments are just capturing the naturally occurring emissions in the layers of the atmosphere. And those instruments, they work on like camera systems, like imagers, or like photometers or Fabry-Perot interferometers. So you might have used these or learned about these in your physics class. But I'm not going to discuss passive techniques in this talk. And then I will show some examples about what are the parameters that we can derive using these instruments, and in the end I will summarize. So what is Earth's atmosphere? So it's the air that we don't see but we feel every day, which is very crucial for our existence. And it consists of 78% nitrogen and 21% oxygen, and the rest is minor species. And why it is important, as I mentioned, that it is very significant for life. It protects us from the harmful ultraviolet radiation from the sun. It forms the ionosphere, which is important for radio communications. And now the question comes, does it vary with altitude? Any idea? Yes, it does. So here is a very basic plot, typical plot of how the atmosphere changes with altitude. So the x-axis is basically pressure or density, and it is increasing this way. This is altitude. So both blue and the red line, they are showing like how density and pressure they fall off as we go higher in altitude. So what it means is like the atmosphere is very dense or thick at lower altitudes, and it becomes thicker it becomes thinner or rarer at higher altitudes. So based on the composition, we distinguish the atmosphere as homosphere and heterosphere. So what is homosphere? So between 0 to 100 kilometers, there is a lot of turbulence in the atmosphere. So the atmosphere is well mixed, and that is why it is called homosphere. Then the turbulence ceases around 100 kilometers. So then after that, the different species of molecular constituents and atomic constituents, they start separating based on the molecular weight because due to gravity. So this results in heterosphere. So what happens in heterosphere is that the lighter species like hydrogen and helium, they are more dominant on the top side. And the heavier species like oxygen and nitrogen molecule are more dominant at lower altitudes. So since in the homosphere, since it is well mixed, the atmosphere follows ideal gas law. So it is like PV is equal to nRT. You must have come across this relation. So both pressure and density are related to temperature. So what does this mean? So do we expect that the temperature should also vary like this? Shall it? Any ideas? Let's see. So the temperature variation is not exponential, but it is much more different than like just the ideal gas law as per like the density exponential variation. And so here, like we see temperature increasing with increasing in the x direction in the right side, and this is the altitude. So up to 100 kilometers. So what is the coldest temperature in this region? What altitude it occurs? it occurs around 100 kilometers. And the warm region is like above 100 kilometers, which is thermosphere. So we are defining these layers based on the temperature. So why there is this variability? So this is explained if you look at the solar radiation that falls on the atmosphere. So what is happening that at higher altitudes, the intensity of the solar radiation is much more higher. But as it propagates to lower altitudes, the intensity is reducing in strength. So that can result in this change because most of the EUV radiation is being absorbed in the thermosphere, which results in high temperatures. And then what is happening is like the lower atmosphere is like much cooler, as I told, because the intensity is dropping. So the troposphere is like where the temperature is lower, but the surface of the Earth is warmer because it absorbs whatever radiation is reaching the Earth. So that's why like at 0 kilometer the temperature is higher. And so what happens? The air above it is cooler. So the air is, because the air which is touching the surface is warmer and starts rising up, and it expands like adiabatically, and it cools the atmosphere too. So troposphere is the region where the weather and climate phenomena occurs. So the cloud formation, thunderstorms, hurricane formation, all these things are occurring between 0 to 15 kilometers or so. And the transition between troposphere and stratosphere is called as tropopause. So then again, the temperature starts increasing in the stratosphere, and this is because of ozone. So at this altitude, ozone forms, and this actually absorbs all the ultraviolet radiation that has passed through from the upper atmosphere, and it protects us. And so this solar heating also generates solar tides. So this is the region where the tides are generated. And then again, the transition region between the stratosphere and mesosphere is stratopause. And mesosphere is the coolest region of the Earth's atmosphere. So why it is coolest region? Because it has like some carbon dioxide. And this carbon dioxide, and as I showed that the density is decreasing at higher altitudes. So when the energy is incident from the solar radiation, the CO2 molecules starts vibrating, but they do not collide because the atmospheric density is like very thin. So what happens during this vibration, they re-radiate at infrared. So when they re-radiate at infrared, it cools down this part of the region, but it heats up the thermosphere, the upper regions, as well as the thermosphere is heated by the EUV absorption from the solar radiation. So that's why it is hotter. So it's very interesting that how solar radiation can affect even the neutral part of the atmosphere and results in the various temperature. And this temperature is a typical profile. But actually, there are a lot of variations that can happen because of other features, like wave activity propagating from lower thunderstorms that can affect even the upper region. So the other thing is that if you look in the lower region, the temperature is decreasing, and the lapse rate. The lapse rate means like how fast it is decreasing with altitude in the troposphere is 6.5 degrees per kilometer. So what is the consequence of this? So this can result in the formation of snow and ice at high altitudes because the temperature is lower and there is water vapor at those altitudes. Yeah, sure.
So the tropopause and mesopause and stratopause is where the temperature is most high.
It is the transition region, like between the two, like two regions. It is the boundary. So it will be like like if you go back, it is like kind of like like this will be the tropopause. So this is the stratopause. And so this also changes. It's not like always at this altitude. There is huge variability, and so it can change, and the temperatures can change also. So these are just like textbook kind of things, but it's like not perfect. Like when we do the experiments, we see like there is no perfect boundary layers. They kind of shift. So what happens, like apart from the temperature variability, what is the other effect of solar radiation? Any idea?
The borealis, the light that goes around the poles that we see, aurora borealis, I think it's called.
Aurora will be seen at high latitudes.
Yeah.
So that is actually particle precipitation.
Mhm.
And so I'm just discussing about like Arecibo, which is a low latitude. So we do not see aurora because the geometry of the magnetic field is different. So the aurora is basically the passive emissions, which are occurring because of they also occur because of the effect of the solar radiations and the particle precipitation during like CME events like coronal mass ejections, or like solar flares, or like when there are magnetic storms, so there will be very strong activity where the strong energetic particles from the sun can enter through magnetic field lines. So I'm not discussing that, but I can explain you later on. So what are the other things? But you were very close to the answer. So ionization occurs above 60 kilometers because of the solar radiation. So you might be familiar with ionization. So here is an example of like hydrogen and helium atom. So hydrogen atom has one electron that revolves around the nucleus. And so when sufficient energy is incident on this atom, that it can knock off one electron and it can result in a H plus or hydrogen ion and a free electron in the medium. And in the case of helium atom, if there is sufficient energy to release one electron, then we have partially ionized helium ion. And in the case like there is more energy which is incident, it can knock off both the electrons, and then we have an alpha particle and two free electrons. So this is how like in the atmosphere we have like ions and electrons apart from the neutrals. So this can lead to the variation of electron density with altitude. So here is a typical profile of electron density at different ionospheric layers. So it shows like the ionospheric layer, they display huge variability. So these are daytime plots, these are nighttime plots. And the solid line represents sunspot maximum, and the dashed line represents sunspot minimum. So sunspot is like related to the solar cycle, and I will show you later on. So first, like we can see that nighttime, the electron densities are much lower than daytime, whether it is solar max or solar min period. So why it is lower during nighttime? Lack of solar radiation. Because the solar radiation is decreasing, so electrons start combining, and that is one reason that you can have the emissions like aurora also, but which will be very weak at our latitudes. So we have to use very, very sensitive camera systems. So as I mentioned that it is related to sunspot maximum. So what are sunspots? So sunspots are these dark spots that occur on the surface of the sun, and they are related to the magnetic field fluctuations. So during the solar cycle, when it is maximum, when the sun is highly active, we see a huge number of sunspots compared to solar min period. And this solar cycle activity, which is represented in terms of solar sunspot numbers, it undergoes 11-year cycles. So you can see like these peaks and these valleys. So these are occurring at 11 years periodicity. And so this can affect the ionospheric behavior too. So now how do we investigate atmosphere-ionosphere system? So one way is to use radio frequencies. And when we use radio frequencies, we have radars, which is an acronym for radio detection and ranging. And then if we use optical frequencies, then we have LiDARs, which is an acronym for light detection and ranging. So I will just briefly discuss, like give an idea about what is radar. So it's a generic system. So in radar, we transmit electromagnetic waves at radio frequencies, and using a transmitter, and when it gets like the pulse or this continuous wave goes up, and it is like scattered from the medium, and the target can be soft target like electrons, free electrons, or it can be hard target like aeroplanes. So there are different kind of radars, and it's very complex. So we have to combine both engineering as well as physics if we want to understand what is happening in this if we want to study atmospheric physics or any like instrumentation, we really need to understand some electronics too. Everything is becoming very multidisciplinary in nature. So what happens is the received power is given by this expression, which is the power, transmitted power, gain of the antenna, scattering cross section, and the area. So what I am trying to make a point here is the received power is very, like usually if we are getting signal from electrons, it is very weak. So if we have a big receiver and a lot of power, then we can even detect very weak signals, which like smaller systems cannot do. And infrared scatter radar at Arecibo with 305-meter diameter was the very powerful system in the world. So I will show some examples like why it was. And the other thing, good thing about the active remote sensing experiments is that when we transmit a pulse in the atmosphere, so we can actually get information about where the return signal is coming from. So how do we get that? This is like very good to understand because it's very basic thing and sometimes people don't understand. So if T1 dash is the round trip time of the pulse, and usually we are recording the signal, and at the receiver room we are collecting the signal at what time it is coming from, what time. So we are recording the time. So we know the round trip time. So round trip time is twice the single way one-way trip time. And the one-way trip time T1 is related to the distance from which it is scattered by this formula RA by C, where C is the velocity of light. So you can calculate this altitude information by this C T1 dash by 2, where T1 dash is the total trip time of the pulse. So by sampling your signal at different times, you will know from which altitude it is coming from. So this is how you calculate, you get the time and altitude information. So here is an example of ISR data, infrared scatter radar from Arecibo. And this is like the received power. So this has not been calibrated. So this is just like the received power. And you can see so this is the E region in the ionosphere. And this is like the peak is occurring around, it also varies. So you can see the variability as I was telling, that ionosphere is not like the typical profiles I showed. They are the average quiet time, but there is huge variability with time and with altitude. So what is interesting is this is daytime. So during daytime, we have enhancements in the layer because of the solar radiation. During nighttime, there is no solar radiation, so the ionosphere is becoming weaker, but it's still E region, we can see these thin layers. And these are called sporadic E layers, and these are actually because of the winds. So if the winds are changing in altitude, they can converge the ions into narrow layers because of E cross B drifts there, and then it's a very complex process, and then they can result in this. So what I'm trying to say, because of the sensitivity of the Arecibo radar, we could actually study these thin layers at night time, which no other radar in the world could do. And we have lost, unfortunately, that thing. So now coming to how do we investigate atmosphere. Also, I forgot to mention that apart from electron density, infrared scatter radar can give ion electron temperatures, as well as we can get ions, the mass of the ions by fitting the spectrum of the return signal. And for this, a lot of theory is required from ISR, and it's a very complicated process. A lot of computational work goes into it. So now I will come to how do we investigate atmosphere. So again, I'm talking about the LiDAR. So in LiDARs, we are using, we transmit UV to near infrared wavelengths. And it usually consists of a laser and a telescope, an optical telescope that collects the backscattered photons, which are directed using an optical fiber to a detector, and the detector can be photomultiplier tube, or it can be APD, like avalanche photodiode, and then it is digitized and stored in the computer for analysis. So this is a basic schematics. It's a simple diagram, but systems can be very complex depending upon what are the things we are trying to study.
Shika, In this case, you do the same as in radio, you make a post.
Yeah, these are pods, yeah.
It's a light post.
Yeah,
and
it's
then
a light
you-
pulse.
You come back to the telescope. You have
Yes,
telescope.
yeah. So it is very similar. The frequencies or wavelengths are different, but the concept of range time, what I showed, will be same. So the observation techniques are based on different scattering processes. So I will just show like briefly the most relevant scattering process that we use in the upper atmospheric work are the elastic scattering, where no change in frequency is observed. And then there is inelastic scattering, for example, Raman scattering, where like you transmit one frequency, but you are receiving at different frequency. But the Raman scattering cross section is very weak. And so when we are dealing with already small cross sections and the density is lower at higher altitudes, so we really need to take advantage of the techniques which have larger scattering cross section. So me scattering from aerosol is very strong, which comes from the aerosol, and it is due to the particle size when it is comparable to the wavelength of the wave that is incident. And then Rayleigh scattering comes from atoms and molecules. So it is like O2 and N2. So Rayleigh technique gives us like it is proportional to the density. And from the ideal gas law for PV is equal to nRT, we can calculate temperatures. So this is another way. So we can have Rayleigh ladder from that. And then we have resonance. So resonance techniques are based on specific atomic transition. So when we send a wavelength, which is resonance wavelength of a particular atom, it will excite the atom into a higher excited state, and when it transitions to the lower state, it transmits back at the same frequency. So that is called resonance scattering. So this can happen if there are metals in the atmosphere. So examples of scattering in life. So Rayleigh scattering. Why sky is blue? Yes.
What are aerosols?
What are aerosols? Yeah, aerosols are like dust particles, like the pollution. That is one reason, and then Saharan dust. Saharan dust that comes, like we feel like allergies and all these things. These are all aerosols. What are the examples of scattering in our life? So why sky is blue? It is because of Rayleigh scattering. So the Rayleigh scattering is inversely proportional to fourth power of wavelength. So what happens since lambda for the blue is much lower than say red? So blue is scattered more, and when the sun is overhead, we are seeing the forward scattering, and the red gets transmitted basically. So sky appears blue because of Rayleigh scattering. And then at sunset, we see that sun is red because when it is at horizon, what is happening? The rays have to travel a lot of distance, longer distance as compared to when it is overhead. So in this case, the blue light, it gets like scattered in all other directions, and the light that reaches us is mostly like reddish and yellowish. And then me scattering. So when there are aerosol or dust particles, Saharan dust in the atmosphere, the sky is not blue, it is hazy. It can be yellowish depending on the particle size. And that is because of me scattering, because me scattering is proportional to 1 by lambda also. And it's like depending on where they are located, overhead or something, there will be also contribution from reddish and yellowish part of the spectrum. So the ladders at AO we have used mainly for the upper mesospheric and lower thermospheric studies. And why we want to study these regions, MLT, we call it MLT, mesospheric lower thermospheric region. So that is like mesosphere starts from 60 kilometers, and with resonance technique we can cover 80 to 120 kilometers. So we are covering mesospheric region and the thermospheric region. So we call it MLT. So because it is one of the least explored region of the Earth's atmosphere, it was actually referred to as ignosphere because it is like too high for balloons and too low for satellites. But recently satellites have, like the frequency of satellites have increased, and so we have more data sets. But the satellites have a good horizontal coverage, but they do not give us good temporal coverage. So everything complements each other. And many satellites were launched keeping in mind that Arecibo existed, and they are now crying because like, yeah, they were thinking that they would get more information using Arecibo ISR and Arecibo systems.
Where is the ionosphere?
Yeah, ignosphere, because there was not much information about this MLT region. Mesospheric or thermospheric region was not easily explored because there were not many instruments in the past. And resonance lidars are also, there are very few because they are a little expensive and there are a lot of manpower required to operate them, and the technology is still evolving. So other reason for studying MLT region is like it is also it gets affected from the solar radiation, as I showed you earlier, and it also gets affected from the waves that are propagating from lower atmosphere. So Arecibo is very unique in that way because we have convective activity. So during thunderstorm, hurricanes, like there are like shock waves or there are waves that are generated that can reach up to like higher altitudes and generate secondary waves, affect the turbulence, and then it can affect the circulation of the entire atmosphere. So it acts like a coupled system. So that is the reason like why it's important to make measurements of these regions. And of course, I mentioned that it is coldest part of the Earth's atmosphere, and other reason is that in this region we have the occurrence of metals, neutral metals and their ions. So what is how metals get deposited? So how many people here have watched Leonid shower? Leonid shower, meteor showers, or have almost everyone. Yeah, exactly. So when meteor enter, we see these trails. And so what happens? So when meteor is entering Earth's atmosphere, so it encounters, as it comes down around 80 to 120 kilometer, it encounters the increasing density. And then because of the frictional heating and the high velocity of the meteor, the temperature of the meteoroid increases, and it can ablate the different metals. So this is how different metals are deposited.
Okay, the deposit of the metal comes from the meteor that are dissolved in the atmosphere.
Exactly. So such metals are like, so these meteors are like from comets and asteroid belts usually. So the metals actually, their abundances are related to the abundances of the comets or the asteroids. And so these metals can be like iron, magnesium, sodium, calcium, potassium, and their ions.
I have a question, Shika. When I know that the atmosphere, when they talk the climate, that in the lower part, there is a circulation of in the planetary level. In the upper level, you have also an horizontal circulation of
Yes.
the atmosphere. And then when you study from Arecibo, you are having the information of this.
Only one very small location.
And then you compare that to other information on the planet, it looks similar how it works.
Yeah, there is a lot of latitudinal variability.
Okay.
Yeah. So like I will show you like not really too much, but there is seasonal variability also, like summer to winter variability, and also there is like the high latitude is very much different from equatorial region, from Arecibo, because Arecibo is unique in a way because the magnetic field configuration here was like 45 degrees. So geomagnetically it is like mid latitude, and geographically it is low latitude. So the ion neutral coupling is very interesting from Arecibo. That's the other thing. But yeah, there is a lot of that's why like when satellites are going through, they give us like the distribution of the species, distribution of temperature, and they have revealed like what is the horizontal variation of different things. Yeah.
So the metals inside the meteors, the asteroids, the metals are inside of them, or they form while they are entering the atmosphere.
No. They are comets and asteroids. They have they have metals. This is the origin of like universe. Like even Earth, our Earth will be having like lot of minerals and other things. So when different planets were formed during Big Bang time. So the composition, the basic composition, I think, of everyone is kind of similar. That's the thing. And so it can date back to like when the people have like tried to estimate the age of the meteoroids and comets by collecting the samples, and doing mass spectrometer analysis in the lab. So we are not doing that. We are using these metals just as a tracers to study the dynamics of this region. And I will show you how do we do. So every metal has a unique resonance wavelength. So if we can tune our laser frequency or wavelength to the resonance wavelength of one of the metals, then we can explore the density of that in the mesosphere, and then it is also like it will vary with the dynamics, like electron density varies with dynamics with the waves. So here is an example, like why do we want to study the metal layers? So because these metals, they act as tracers for studying dynamics, chemistry, and temperature of this region. So the return signal will have information about these parameters. And by like combining different lidars and ISR, we could study the coupling between neutral and ionized species, which allowed us to study like how they interact, the neutral and the neutral atmosphere and the ionosphere. We can also compare different metal layers, like if they behave similarly, because if the chemistry is different, the layer properties will be different. And then we can also study the coupling between different regions of the atmosphere. Because
when you do the observation, you observe one particular species at the time, or how you do that?
yeah, I will show it to you. So observations are required for developing models and validating the models. So here is an example of the complex chemistry processes that occur in the MLT region. And this work was published by a German group, Görding et al. In 2000. So if we want to validate this model, we have to constrain different constituents. We really want to have as many parameters that we can observe from the instruments to constrain the models. And so the parameters that can be observed from grounds are neutral calcium ion using the LiDAR, and electron densities using the ISR. And Ca plus is the only ion that can be observed from ground, because the other ions like Na plus, Mg plus, Fe plus, which are more dominant than Ca plus, they all have resonance wavelengths which fall in deep UV and are attenuated by ozone. So we cannot observe them from ground-based lidars. So I mentioned that ISR provides electron density profiles, and resonance lidars gives us Ca and Ca plus profiles. So there are several instruments at Arecibo. There are like 3 kind of lidars for upper atmospheric world. And so of course the lasers are like used for the transmitters. So we have like Alexandrite system. I don't work with that system. My other colleague works, and it is tuned to potassium atoms at 770 nanometers. And it is a narrowband system, and it can give us potassium densities as well as temperature. Potassium is very low in meteoroids, so the density is low. So wind measurements are not possible. For wind measurements, the best species is iron. So that's why we cannot do winds from this. And then there are 2 identical high-power Nd:YAG lasers, which are commercial lasers on which I am working with, which can be used in either relay mode to give the temperature from stratosphere to mesosphere, or they can pump 2 lasers that can be tuned to different wavelengths. So that's how like we have studied, like we can study 3 metal species together along with ISR. So that made Arecibo a very, very unique place. And these are like some photos of the instruments. And I wanted to show a video of the laser operating in the lab. So you can see like green light and yellow light. So the yellow is from the sodium, and the green light is pumping the dye laser. So this is an example of LiDAR and ISR data. So this work was published in 2011 in GRM, and this is an example, like the 3 nights are shown here in 3 different panels. They are adjacent night. The upper panels are from ISR and are showing the electron density variation during nighttime. And these 2 are like the LiDAR data sets. This is the calcium ion and this is calcium atom. So see, we have all the 3 together for the first time in the history. And so we could actually try to validate the model. So this work allowed us to calculate the lifetimes of Ca plus ions using that model. So we used the Girdings model and found that the Girdings model that I showed you earlier overestimated the lifetimes. So then we collaborated with some other modelers, and then they tweaked the model to provide us the reasonable lifetimes, because like if you look at this plot, so calcium neutral is increasing in density while the Ca plus and the electrons are decreasing. So what it is showing that when ions are decreasing, atoms are increasing, so it is showing ion neutral coupling. So it means that there is neutralization happening at very fast time. So the earlier model showed that it was happening much slower, but then it speeded up, and so it was. Then we found that with the new model, we had like at 95 kilometers, which is around this altitude, the lifetimes were very fast, of the order of few tens of seconds, and the ions lifetime can increase exponentially at higher altitudes, which means they have very long lifetimes. So they do not neutralize very fast. So this was a very good contribution from Arecibo, that Arecibo only could do because of ISR. And then, like as I mentioned, that somebody asked like how the metals, like are they? So the metals are there in the meteoroid, which comes from the origin of the universe, and they are just like how they are ablated is shown here. So this is based on a model which was developed by Plain, and it's called CABMOD, chemical ablation model. And what it shows is like when a meteoroid which 5 microgram enters the Earth's atmosphere at a speed of 20 kilometers per second, then how the different metals are released, at what altitude they are released, and what are the temperature they are reaching. So the ablation temperature is 1500 Kelvin. So it should reach 1500 Kelvin, and that actually is more than 1500 Kelvin can be achieved only at lower altitude. So you can see that the metals like calcium, iron, magnesium, they are being released below. So you don't expect metals to be there beyond like 120 kilometers because the ablation efficiency is not good. So, but recently with a very interesting and like more integration time and sensitive LiDAR systems, people have seen metal layers, neutral metal layer extending up to 155 kilometer, 170 kilometer. And this is from Antarctica, and this is from Chile, and this is from Arecibo. So what happened? These this group, when they observed Linzhou 2 from Antarctica, they postulated that this is because of the neutralization of the ions. But we have shown that neutralization of ions is not like very efficient process at higher altitudes. So we looked at our data set and we found that we were running sodium and potassium LiDARs together along with ISR. And this work appeared in 2015 in GRL. And what it shows is the layer descent rate is very different from the ion descending layers seen in the incoherent scatter radar. So it means like these layers were not, at least for that event, they were not related. They were not coupled, they were separate. So the processes that are responsible for the occurrence of these metal layers at higher altitudes is still intriguing, and there might be some latitudinal variation. So this is like an ongoing puzzle. So one of the things was that none of these, like these groups, they didn't have any information about metal ions or electron density. So they couldn't they were just assuming things. So Arecibo had metal ions. So we were lucky. In 2016, we had upgraded our systems So we were able to detect, we were running like 3 LiDARs and with ISR. I'm not showing the other 2 LiDARs. What I'm focusing here is calcium ion, which is shown here. And the above panels are the electron density data from ISR. So you can see that during the early morning hours, like at 4 a.m., like we have these interesting structures in Ca plus ions above meteor ablation zone. And these were like located at the edge of these descending layers, which was seen at ISR. So this was like very interesting because there were no neutral matters detected above 120 kilometers. So since I mentioned earlier that ions have long lifetimes, so this appears to be related to transport processes. And like I'm trying to work on a different paper, analyzing more deeply, that it might be related to equatorial region, transport from the equatorial region. So there is an ISR at Jicamarca, Peru, which is like not as like, now it is the most powerful that are after Arecibo. But the thing is, equatorial region has different phenomena compared to high latitudes and mid latitudes. So they have their ionosphere is very different from Arecibo because they have something called equatorial spread of irregularities. And they have a lot of plasma irregularities because the magnetic field is horizontal at the equator. Here the magnetic field is like this. At the high latitude where aurora occurs, the magnetic field is vertical. So, you know, there the magnetic particles, the energetic particles from the solar emissions can enter very easily, you know, depending on the magnetic field configuration. So they enter from there. But here at equatorial, it is horizontal. So there is E cross B drift and plasma instabilities, different kind of processes are occurring. So they have like coherent echoes instead of incoherent echoes. So coherent echoes, they come from when there are structures in the medium. So it's like, it appears like, you know, when instead of a single electron radiating back, you have like bunch of plasma behaving as like a solid particle. So together, so the scattering cross section is like knee scattering, very high. So you have strong scattering, so you cannot resolve some of the things that Arecibo can resolve. So yeah, but what I'm saying that during ESF, during equatorial spread of irregularities, so ionosphere has like these perturbations in the electron density, and it can affect radio communication. So sometimes like we are listening to radio and there are fade off in the signals. That is because our ionosphere is going through some perturbations. So we think that it might be related because we found that there was ESF irregularities in Jicamarca. So they can lift the ions to higher altitudes because of E cross B drift from the E region, and then the wind can transport them to Arecibo. This is what like. So apart from this, there are like other comparisons of the LiDAR data from Arecibo that we have made, and these are like different nights. So these are neutral calcium data, and we compare here with potassium data sets. So on the first night, it is very interesting. You can see like there is enhancement and the layer is like descending in neutral calcium, but potassium is very weak. So this was very interesting. So we try to explain it based on the differences in the temperature dependent chemistry that time. So another example here is about like how the sodium layer changes. So this is like, this plot shows like time and this is altitude. And you can see like the enhancement, like how it is broader. This is for one particular night. And then like we use all the summer and winter data, average them together in time, and then try to see what are the characteristics of the layers during summer and winter. And we find that during summer, the layers are broader, like the peak is much broader and persistent all through the night. But in winter, like we have, initially it is broader for some time, then it kind of becomes thicker, and then it is narrower. So there are like differences, monthly variations, daily variations, and also the latitudinal variations that I'm not showing here because of time limitations. Then other thing is like high resolution data can allow us to study like events. So you see like these beautiful features here. We call like them billows or overturning. And have you seen, like, what is the altitude? This is occurring around between 93 and 94 kilometers. Have you seen this in the sky, in clouds? You should watch sky. I will show you. Yeah, sometimes when I'm looking at the sky, I'm looking at the clouds and they are like displaying very nice features. These are the photos of the clouds. See how much resemblance is there between the upper and the lower atmosphere. So what I'm trying to say, like, by understanding different fields, we can apply our knowledge to that field. And it seems like these features can appear when the atmosphere becomes unstable. So it can become unstable because of convective instabilities, because of temperature variations, or because of dynamic instabilities, because of wind shears. And then in case of mostly it is wind shears. And they give rise to, like, the shears, like they give rise to Kelvin-Helmholtz instabilities. So Kelvin-Helmholtz instabilities can give rise to such features. And this night was very interesting. I will show you like a movie. So you see this movie, you see like these here, like these billows, set of billows that I had shown earlier. And then you see how there is another one here. And then you can see like how the layer is like striations in the above. And then again at the edge here, 1, 2, 3, 4. They are not very clearly seen because of the projection. Then you see here, very nice. Boop, boop. Then here at the edge, you see 1, 2, 3. And then later on, the atmosphere, like the layer was behaving like atmospheric ocean waves. So there is like, someone told me when I showed it to one scientist in a meeting, they showed that, look at the ocean wave papers, and you may get some insights about it.
They look like waves.
Yes, yes. So, and we are talking about very high altitude. So there are a lot of other applications of LiDARs. So I will just briefly show. So one of the application is nowadays in agriculture and land mapping. So how it is used, it can be used for identifying areas that has optimal sunshine, and then you can have like efficient growing. And it can be used to train machine learning algorithms to identify crops that need water and fertilizer. It is also used in archaeology. It helps experts discover hidden structures through scanning the earth. And climate change, of course, like calculate changes in the glaciers over time and track atmospheric gases, gives information about aerosols. And this has been done from the space also. It has been used in astronomy. So NASA has used LiDAR technology to explore Mars. They created a topographic map and detect snow falling in the atmosphere. And of course, nowadays it is used in automated self-driving cars. And that is a relatively new application, and it requires a lot of machine learning algorithm because like you are collecting a lot of information and the machine learning will detect very fast, like if there is a target there and so on. So what I'm saying that it is very, like everything is multidisciplinary. You need to understand digital optics, some electronics, not too much, some physics. Of course, computer programming is must. Is must. And if you want to do machine learning, Python is very, like nowadays, I was using Ideal, but like during COVID time, I took courses online and should switch to Python. So I'm trying to say is like you guys are young. If I can do it, you can do it. So computer is something like software is something that is very crucial if you want to go to any field, and it will be very good for your academic growth. So keep your mind open, and you can always apply your knowledge to other fields. And I didn't discuss plasma instabilities and other things. They occur even in astrophysical plasma. And so yeah, plasma physics is other thing which is very important from like ionospheric point of view, because ionosphere access natural plasma laboratory. So to summarize, atmosphere is divided into different regions based on temperature, and weather phenomena occur in the lowest region, which is distinguished as troposphere. Mesosphere is the coldest region of the atmosphere. Ionosphere exhibits huge variability in electron density distribution, and it depends on the solar activity. And it also displays day to night variation due to lack of solar radiation after sunset. Different metals occur in the mesosphere and lower thermospheric region. They are deposited through meteoric ablations and are used for studying the dynamics and energetics of the region. Ladder provides like information, as I mentioned, about MLT region, and they have been used in other remote sensing of other areas, which have like wide applications in agriculture, in automated cars, and many other fields that I have not discussed here. So acknowledgements are like, of course, to NSF for providing financial support, to entire AO staff, because I alone cannot do this work. And some of the photos and videos were taken from these sites. They are available and you can explore. And thank you, and questions are welcome.